Dear students, so today let us study about a new topic known as non-aqueous solvents. We have already studied the meaning of a solvent in earlier classes. So we have studied a solute, solvent and solutions. The substance which is present in smaller quantity in a solution is called solute. The substance which is present in larger quantity in solution is called solvent. And the mixture of solute and solvent together, a homogeneous mixture, is called solution. This is you have studied in lower standards. Now, the solvents are generally also used to carry out the reactions. Many reactions we carry out in water medium. Then the water becomes a solvent. Similarly, the many reactions, the organic reactions, we carry out in benzene, in acetone, in alcohol, etc. These also becomes the solvents. Here, the word non-aqueous solvents. Aqueous means water. Now, the solvent without water is non-aqueous solvents. These may be organic solvents or it may also be the inorganic solvents. Of course, the organic solvents like benzene, alcohol, ether, acetone, etc. These also will be the non-aqueous solvents which are generally of organic nature. But the today's class, it deals with non-aqueous solvents which are concerned to inorganic systems. So, the non-aqueous solvents, before to know about it, let us know the classification of the solvents. Solvents have been classified in a number of ways depending on their physical and chemical properties. Three important ways of classification of solvents are: number one, Protiq or Protonic solvents; number two, Ionizing solvents; and number three, aqueous and non-aqueous solvents. Now coming to the first one, Protiq or Protonic solvents. These solvents have hydrogen atom in their formula. The word Protiq refers to hydrogen. There are two types of the Protonic solvents. One type is acidic or protogenic solvents and another type is basic or protonic solvents. Protogenic solvents have strong tendency to donate protons. Example: sulfuric acid, hydrofluoric acid, acetic acid, hydrocyanic acid, etc. The protonic or basic solvents have strong tendency to accept protons. Like examples: ammonia, cyclopentane, amines, hydrazine, that is N2H4 is hydrazine, etc. Coming to the second type of this, called aprotic or non-protonic solvents. The word itself says means non, or non means there is no hydrogen ions. These may or may not have hydrogen in their formula and neither donate nor accept protons. Example: benzene, chloroform, sulfur dioxide, carbon tetrachloride, bromine trifluoride, etc. The third type of this class is Amphiprotic or Amphoteric solvents. These have hydrogen in their formula and may or may not donate or accept protons. Hence, these can act both as acids and bases. Hence the word amphoteric. For example, the water. The water contains H plus ion and OH minus ion. H plus ions are present in acids, OH minus ions are present in bases. Since this solvent is having both these ions, hence this is amphoteric in nature. The another example is acetic acid. In acetic acid, the H attached to the COH group donates the proton, but whereas the H attached to the methyl carbon, they are not going to donate the protons. Coming to the second class, that is known as ionizing solvents. In this class, these are polar or ionic in nature. Ionic compounds dissolve in these solvents. These solvents are weak conductors of electricity and have high dielectric constant. These solvents undergo self-ionization. The examples of ionizing solvents are the water, ammonia, HF, hydrofluoric acid, sulfur dioxide, etc. Coming to the examples of this, ionizing solvents like water. So water, it turns into the H plus and OH minus, NH3, NH4 plus ion, HF, H plus, F minus. So SO2, SO plus, SO3 minus. As I have said, NH3 becomes NH4 plus and NH2 minus, etc. Non-ionizing solvents. These are non-polar or non-ionic in nature. Hence, dissolve only non-polar or neutral compounds. These solvents do not undergo self-ionization and have low dielectric constant. Organic solvents are the examples of this kind. Benzene, carbon tetrachloride, toluene, etc. are the examples of non-ionizing solvents because they do not undergo ionization. Coming to the third type, that is aqueous and non-aqueous solvents. If water is used as a solvent in a reaction, it is called aqueous solvent. The solvents other than water are called non-aqueous solvents. Example, liquid ammonia, liquid sulfur dioxide, liquid hydrofluoric acid, etc. Like water, non-aqueous solvents also undergoes self-ionization or autoionization. So, if you take the water, the two molecules of water, it undergoes dissociation to form H3O plus known as hydronium ion and OH minus known as hydroxide ion. Similarly, the two ammonia molecules undergoes ionization to form ammonium ion and amide ion. The sulfur dioxide undergoes ionization to form the sulfite ion and the SO2 plus ion. It is called sulfoxide ion. Now let us we study in detail about the liquid ammonia as a solvent. Liquid ammonia is one of the most water-like solvent. It is also an example for protonic solvent and is able to dissolve a wide variety of substances. Melting point is 175.3 Kelvin, boiling point is 239.6 Kelvin, dielectric constant is 23, specific conductance is 5 into 10 raised to minus 11 per ohm per centimeter. Now, let us take some of the properties of this liquid ammonia. The first one, solubility of substances in liquid ammonia. Since the dielectric constant of ammonia is much less than that of water, hence liquid ammonia is a poor solvent for ionic compounds. It means to say the majority of the ionic compounds are soluble in water, as we say, because water is a polar solvent and also water is having high dielectric constant. Since liquid ammonia is having comparatively lower dielectric constant, so the dissolution of ionic compounds in liquid ammonia is comparatively less. Nitrates, thiocyanates, perchlorates, cyanides, iodides, hydrocarbons are soluble in liquid ammonia. Oxides, hydroxides, sulfates, carbonates, phosphates and sulfides are insoluble in liquid ammonia. Alcohols, chloroform, ketones, esters, ethers and phenols are soluble in liquid ammonia. This is about the solubility of the liquid ammonia. Coming to the second one, known as autoionization of liquid ammonia, or it is also called self-ionization of liquid ammonia. Like water, liquid ammonia also undergoes autoionization. The water, it undergoes ionization to form hydronium ion and hydroxide ion. Similarly, the liquid ammonia also undergoes autoionization to form ammonium ion, that is NH4 plus, and amide ion, that is NH2 minus. The extent of ionization is less than that of water. This is once again due to low specific conductance and less ionic product. We know the ionic product of water is 1 into 10 raised to minus 14 at 293 Kelvin. Whereas similarly, instead of calling ionic product of water, we call it as ionic product of liquid ammonia is 1.9 into 10 raised to minus 33 at 218 Kelvin, which is much less than that of the water. Coming to the third property, that is acid-base reactions. On the basis of Bronsted-Lowry concept, in case of water, hydronium ion acts as an acid and hydroxide ion acts as a base. Similarly, in case of liquid ammonia, ammonium ion acts as an acid and amide ion acts as a base. If I take the water H2O plus H2O, one H2O is an acid, another H2O is a base. So that base takes the H from an acid and forms H3O plus. It is called the conjugate base of the parent acid. That is called conjugate acid of the parent base. Hence, it is called acid 2. Similarly, hydroxide ion is called the conjugate base of the parent acid. Similarly, the two ammonia molecules turns into the NH4 plus and NH2 minus. NH4 plus is called acid 2 and NH2 minus is called base 2. Coming to the another here, that is known as neutralization reaction in liquid ammonia. So in liquid ammonia, like in case of water, HBr is an acid, HCl is an acid, H2SO4 is an acid, HNO3 is an acid, because in case of water, H makes the acidity. Similarly, in case of liquid ammonia, instead of water the H, here the replaced by NH4. So NH4Br, ammonium bromide, is an acid in liquid ammonia. But whereas ammonium bromide is a salt in water. This is very important point to be remembered, dear students. Ammonium bromide, when you call, you have in your mind ammonium bromide is a salt. But ammonium bromide is an acid in liquid ammonia. Like ammonium sulfate. Ammonium sulfate is just like H2SO4. Ammonium chloride is just like HCl. Ammonium nitrate is just like HNO3. When it combines with, so there we used to call it as NaOH is a base, KOH is a base, NH4OH is a base in water. But in case of liquid ammonia, instead of OH, here we have NH2 minus. So KNH2, that is called potassium amide. This potassium amide is a base. Okay, so ammonium bromide is an acid, combines with potassium amide, which is a base, to form potassium bromide, which is a salt, and forms ammonia. We have studied acid combines with the base to form salt and water. Here also the ammonium bromide is an acid, potassium amide is a base, it forms potassium amide is a base, it forms potassium bromide, which is a salt, and forms a solvent, that is ammonia. Salts react with base in water to form metal hydroxides. Alkali metal hydroxides are soluble, while rest of the other hydroxides are insoluble, which further turns into the oxides. This also you have studied in case of the water. So you have studied in case of water. So alkali metal hydroxides. So alkali metal hydroxides means NaOH, KOH. They're all soluble in water. Okay, but whereas magnesium hydroxide, calcium hydroxide, ferric hydroxide, they're all insoluble in water. And such hydroxides, they also turns into the oxides. Ferric hydroxide turns to ferric oxide. Calcium hydroxide turns to calcium oxide, like this. Similarly, in liquid ammonia, salts react with base to form metal amides, which further turns into imides and nitrides. Here I have given an example. Magnesium nitrate, when it is treated with sodium hydroxide, we get magnesium hydroxide precipitate and sodium nitrate. This reaction takes place in water medium. So that's why in water we get magnesium hydroxide. This magnesium hydroxide, if you heat further, it turns into the magnesium oxide. This is in presence of water. Now similarly, let us we take silver nitrate. When it is treated with potassium amide in liquid ammonia, we get silver amide as a precipitate and gives potassium nitrate. Similarly, lead iodide, when it is a salt, when it is treated with a base, that is potassium amide in liquid ammonia, gives lead amide and potassium iodide. So silver amide and lead amide are the precipitates, just like magnesium hydroxide. So these amides, they further react with the salt and forms imides. Like hydroxides, they turn into oxides. Here amides, they turns into imides. That is PbNH is lead imide. This which further turns into the nitrides. The example I have given, mercuric iodide, when it is treated with potassium amide, we get Hg3N2, known as mercuric nitride. Many metal amides, imides and nitrides dissolve in potassium amide solution in liquid ammonia to form complexes. So this is also just like the aluminium oxide. So aluminium oxide, when it is treated with NaOH, it forms sodium meta-aluminate NaAlO2, which is soluble in water. In a similar fashion, so silver amide, when it is treated with potassium amide in liquid ammonia, it gives KAgNH2 twice. That is the potassium diamide argentate 1. Now coming to the another property called precipitation reaction. This precipitation reaction is also called metathetical reaction. Students, you have to remember this. Precipitation reactions are also called metathetical reactions. A large number of reactions which do not occur in nature have been reported to be carried out in liquid ammonia. This is because of the difference in the solubilities of various substances in liquid ammonia and water. Example, in water, barium chloride is soluble and silver chloride is insoluble. This reaction you have studied in the qualitative analysis. That is the test for the chloride is, you take the barium chloride, add silver nitrate, gives silver chloride precipitate. That means barium chloride is soluble in water and silver chloride is insoluble in water. Hence, silver chloride will not react with barium nitrate to form barium chloride once again. However, in liquid ammonia, this is exactly the reverse case. So, silver chloride is insoluble in water, but silver chloride is soluble in liquid ammonia. Barium chloride is soluble in water, but in liquid ammonia, barium chloride is insoluble. This is the beauty of this precipitation reaction. So there it is given the same thing. So the silver chloride, when it is treated with barium nitrate in liquid ammonia, gives barium chloride precipitate and silver nitrate. Similarly, potassium chloride is soluble in water, but it is insoluble in liquid ammonia. Example, Ki plus NH4Cl in liquid ammonia gives KCl as a white PPT plus ammonium iodide. Coming to the next property, that is called complex formation reactions. Many complex formation reactions have been reported which are similar to reactions occurring in water systems. Example, when potassium cyanide is added to silver nitrate in liquid ammonia or in water, a precipitate of silver cyanide is formed, which dissolves in excess of potassium cyanide to form a complex compound of potassium argentocyanide. So this reaction takes place in water as well as in liquid ammonia in a similar fashion. So silver nitrate, when it is treated with potassium cyanide in liquid ammonia, gives silver cyanide as a precipitate and potassium nitrate. This silver cyanide further reacts with potassium cyanide to form the potassium argentocyanide. The IUPAC nomenclature of this is potassium dicyanoargentate 1. Coming to the sixth, is called Amanolysis reactions. This ammonolysis reaction is nothing but it is just like hydrolysis in case of water. This is what I have written. This reaction is similar to that of hydrolysis in water. In general, it is also called solvolysis. Liquid ammonia is regarded as an ideal solvent for many ammonolysis reactions. Alkali and alkaline earth metal hydroxides are ammonolized to the corresponding metal amides and hydrogen. For example, sodium hydride, when it is treated with ammonia in liquid ammonia medium, we get sodium amide and hydrogen. Similarly, magnesium hydride gives magnesium amide and hydrogen. Many covalent halides undergo ammonolysis in liquid ammonia. Mercury chloride undergoes ammonolysis to form mercury amidochloride, HgNH2Cl. Silicon tetrachloride in liquid ammonia gives silicon tetramide. Similarly, germanium tetraiodide in liquid ammonia gives germanium tetraamide. Last point, that is the one more, that is called ammonation reactions. Ammonation, this reaction is similar to that of hydration in water. In general, it is also called solvation. We have studied copper sulfate pentahydrate CuSO4 0.5H2O. So, like this, Al2O3 0.2H2O, which is a bauxite, it takes 2 water molecules as water of hydration. So, in case of copper sulfate, it takes 5 water molecules as water of hydration. Similarly, we also have ammonation reactions. Boron trifluoride in liquid ammonia, it takes 1 liquid ammonia molecule and forms, so boron trifluoride monoammoniate or boron trifluoride monoammonation. Similarly, silicon tetrafluoride takes two ammonia molecules and forms silicon tetrafluoride diammonate. Similarly, sulfur trioxide forms sulfur trioxide diammonate. So this is about what exactly you have to learn in liquid ammonia and its various properties. Now the same thing I have given in this slide, the introduction of the inorganic non-aqueous solvents and what is non-aqueous solvent and its types. I've said about aprotic solvent, protogenic solvent, protophilic solvents, amphiprotic solvents. So this is another way of classification. So here also I have said the meaning of the protonic and non-protonic solvents. That explanation is once again given in this slide. Here also I have said the liquid ammonia as a non-aqueous solvent, and they're all the physical properties. Their freezing point, boiling point, dielectric constant, all the properties are shown here. In case of the reaction in liquid ammonia, we know the acid-base reactions. So the acid reacts with the base to form salt and water. So here also in liquid ammonia, how this ionization takes place. And also proteolysis reactions. So here we have given solutions in liquid ammonia. So many compounds, they dissolve in liquid ammonia and forms the solutions. And in the next below I have given the types of reactions in non-aqueous solvents. As I have said, metathetical or precipitation reactions. I have discussed this. That is the silver chloride, which is a precipitate in water medium. The same silver chloride is soluble in liquid ammonia. Barium chloride, which is soluble in water medium, the same barium chloride acts as a precipitate in liquid ammonia. So we also have ammonolysis reactions, what we have discussed earlier. And also we have acid-base neutralization reactions. So various examples are given here. And also we have precipitation reactions once again here. And lastly, you must know why ammonia acts as a better solvent than water. Ammonia acts as a better solvent than water. It is due to the poor conductor of electricity, the first one. The second, specific heat of ammonia is greater than water. Liquid ammonia is less viscous than water. It has high critical temperature and pressure. It is less associated than water due to lesser hydrogen bonding. It is due to formation of strong reducing metal ammonia solutions with alkali metals. So this is also given here, and dear students, go through these aspects and try to learn. It is a very fantastic way you can learn, and if you go on comparing with water, you can understand much better.